And with that, let's proceed with our lesson for today, and that is nuclear chemistry. For today, we will discuss atomic species and nuclides, nuclear stability and binding energy, nuclear radiation and radioactive decay, kinetics of radioactive decay, and nuclear reactions. Okay, G? G ba guys? Sagot nga. G na. Okay. So this figure shows the nucleus of uranium. Recall our lesson on atomic structure. Ano nga ba ang ulit composition ng nucleus? Yes, it consists of protons and neutrons. So in this chapter, we are going to discuss atomic species and how they vary or react depending on the number of neutrons and protons they have in their nuclei. So let's describe atomic species and nuclides. Nuclides are atoms with a specific atomic number and mass number. Recall guys, atomic number is Z, mass number is A. Every nuclide is unique because of its combination of nucleons. Now, nucleons, guys, is just a general term that refers to either a proton or a neutron. Now, together, the nucleons make up the mass of an atom's nucleus. Okay? And that's what we aim to study in nuclear chemistry. Now, there are three types of atomic species, namely isotopes, isobars, and isotopes. Right. So, nagkakaiba sila based on these following criteria. So first, isotopes, same elements are involved. For isobars, different elements are involved. For isotopes, different elements are involved. In terms of atomic number, equal ang atomic number ng isotopes. For isobars, different ang atomic numbers nila. For isotopes, different ang atomic numbers nila. For mass number naman, okay, different ang mass numbers ng isotopes, equal ang mass numbers ng isobars, and different ang mass numbers ng isotopes. Next, for the number of neutrons, different ang number of neutrons ng isotopes, different din ang number of neutrons ng isobars, and equal ang number of neutrons ng isotopes. Now, for the chemical properties, okay, similar ang chemical properties for isotope, different for isobars, and different for isotopes. For the physical properties, different ang physical properties ng isotopes, similar for isobar, and different for isotope. So examples of isotopes include carbon-12, carbon-13, and carbon-14. As you can see guys, pareha sila ng Z or ng atomic number. So when I say that these three elements are isotopes, they have the same atomic numbers. Next, tin, tellurium, tin 124, tellurium 124, and xenon 124, they are all isobars. Okay? Meaning that they have the same mass numbers equal to 124. Okay? And lastly, we have silicon 30, phosphorus 31, and sulfur 32. Now when I say that these three elements are isotopes, they have equal number of neutrons. Okay, let's proceed. So here we have isotopes. Guys, recall nyo sa bridging nyo, di ba nag-discuss na on isotopes, may some examples na kayo. So now let's delve into it deeper. Again, atoms of the same element or same atomic numbers ang isotopes. And an example natin dito are the three isotopes of hydrogen, protium, deuterium, and tritium. Okay, same elements sila, right? And they all have the atomic number 1. Pero they have different mass numbers. So protium is hydrogen 1, deuterium is hydrogen 2, and tritium is hydrogen 3. Okay? And guys, remember, if you see an element, then may dash tapos number, yung number na yun, okay, ito, represents the mass number. Again, mass number is the sum of neutrons and protons. Okay? Next, we have the isobars. So, isobars refer to different elements with different atomic numbers but equal mass numbers. So, examples are sulfur, chlorine, and argon. So, all of them have a mass number equal to 40, as you can see here. So, si sulfur 40, chlorine 40, argon 40. Okay? Kasi yung sum ng protons and neutrons nila ay lahat 40. Right? Okay. Lastly, we have isotopes. So, isotopes are different elements with different atomic numbers and mass numbers. So, magkaiba ang A and Z nila. But all of them have equal numbers of neutrons. So, for example, we have the isotopes of silicon, 30, phosphorus 31, sulfur 32. Okay? Lahat sila, magkaiba ang mass number, magkaiba din ang atomic number, right? But they all have equal number of neutrons. Guys, take note ha, important talaga itong atomic species. Alam niyo bakit? Dahil lumabas to nung board exam 2023, so nung time to. Okay? May tanong about which of the following are isotopes? Ganun. Tapos, wala akong nasagot kasi hindi ko alam yung meaning ng isotopes. So now you know. Okay? Okay. So let's proceed. Now, before we go on to the nuclear stability, okay, so that's the stability of nuclides, kindly watch this video to understand the concept.
So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what time will occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta-minus decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta-plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay.
Okay guys, so let's proceed since we now know the basic concept of nuclear stability. So now, how do we exactly determine the nuclear stability? How do we know if a nuclide will undergo radioactive decay or not? So this is through 1, the number of nucleons, and 2, the neutron to proton ratio. Okay, so kailangan natin guys, mahanap yung number of neutrons and number of protons to get the neutron to proton ratio. So table 11 summarizes certain characteristics of stable and unstable nuclides para madali niyong maspot. So hindi to requirement guys, okay? So parang ito lang yung typical characteristics ng unstable nuclides, tapos ito naman yung typical characteristics ng more stable nuclides, okay? Hindi siya requirement. Pwede lang na may characteristics sila na ganito. First, for unstable nuclides, typically they have an atomic number greater than 84. Okay? Next, unstable nuclides can have odd number of protons and neutrons, and unstable nuclides can have an N/P ratio greater than 1. Next, more stable nuclides naman have atomic numbers less than 20, and dahil dyan, their neutron to proton ratio is equal to 1. Second, more stable nuclides have an even number of protons and neutrons. Lastly, more stable nuclides can contain magic numbers. So, hindi ito requirement ha. Basta kung may magic number yung nuclide, then that means stable siya. Okay? So, the magic numbers include 2, 8, 20, 50, 82, 126 protons or neutrons. So, for example, we have helium. It has 2 protons, 2 neutrons, right? So, dahil dyan, meron siyang magic number. That's why we can say helium is stable. Next, calcium-40 has 20 neutrons plus 20 protons. Okay? Meron din siyang magic number. That's why we can say it's a stable nuclide. Lastly, dito ko na lang sulat guys, PB208 it has 82 protons plus 126 neutrons. Okay? Double magic number yan, di ba? So that's why lead-208 is known to be one of the most stable na heavy nuclides. Okay? And with this, guys, the following table, table 12, summarizes the approximate value for radioactive decay prediction. So ito na yung ginagamit natin, ang neutron to proton ratio. Okay, let's start. Now, if atomic number is greater than 83, so guys, usually ang gagamitin natin for unstable nuclides, 83 na lang, kaysa nito, 83. Some references would say dapat C is greater than 82 or 84, but now let's just use 83. Okay, so if the atomic number is greater than 83, then alpha decay occurs for the nuclide. Now, beta decay occurs naman for nuclides na may neutron to proton ratio na greater than 1, greater than 1.25, and greater than 1.5. Then positron emission or electron capture occurs to nuclides with an N/P ratio na less than 1, less than 1.25, and less than 1.5. Guys, magdedepend lang kung alin dito ang pipiliin na comparison depending on the atomic number of the nuclide. So kunwari, yung nuclide mo has an atomic number equal to 40. So part siya ng range nito. So kung hanapin mo yung neutron to proton ratio ng atomic number na ito, over T, check nyo if it is less than or greater than 1.25. Okay? So for example, guys, let's say you have a nuclide with atomic number around this range, 41 to 82. Okay? So yung neutron to proton ratio niya, if it is greater than 1.5, then the nuclide will undergo beta decay. But if the N/P ratio for the nuclide is less than 1.5, okay, the nuclide will undergo electron capture. Tandaan nyo to, guys, ha? Pag ang nuclide has an atomic number greater than 40, so that's 41 to 82, then that means electron capture yung decay niya. Okay? Hindi positron emission. Okay? With that, let's try the sample problem. Predict the type of decay for the unstable nuclide I-125. So sabay-sabay muna tayo. So the number of protons for iodine is 53. Number of neutrons is 72, since 125 minus 53 is equal to 72. Next, let's find the N/P ratio. So let's just N 72 over 53 equal to 1.36. Next, refer to this table, guys. Check nyo muna yung atomic number ng iodine. Diba is 53. So, nandito siya sa range na to. Therefore, i-compare nyo ang N/P ratio na to kung less than 1.5 siya or greater than 1.5. Since 1.36 is less than 1.50, okay, then the nuclide will undergo electron capture. Okay? Gets ba so far, guys? So ito yung ginamit ko na basis, okay? Dahil ang atomic number ni iodine ay 53, which is within 41 to 80. And again, pag greater than 40, ang atomic number ng nuclide, okay, ang pipiliin nyo sa dalawang to ay electron capture. Pero kung less than 40 naman, let's say nasa 20, ganun, tapos less than 1 siya, then positron emission. Okay? Okay, next example. Kayo naman mag-try, guys. Pause the video first and try it. Okay, so let's start. So the number of neutrons for sulfur is 35 minus 16 equal to 90. Number of protons is just atomic number, is equal to 16. Finding the neutron to proton ratio, 19 over 16 is equal to 1.19. Now, the atomic number of sulfur is 16, right? So it is within this range, 1 to 20. So, i-compare nyo lang if 1.19 is greater than 1 or less than 1. So which is it? Tama, 1.19 is greater than 1. That's why sulfur 35 will undergo beta decay. Very easy, right? Okay, next. Predict the type of decay for the unstable nuclide uranium-238. Okay, pause nyo muna the video and try that. Okay, let's answer. So, uranium-238, ang kanyang atomic number ay 92. Oops, that is greater than 83. Therefore, uranium-238 will undergo alpha decay. Lastly, predict the type of decay for the unstable nuclide carbon-11. So for carbon-11, its number of neutrons is 5, since 11 minus 6 is equal to 5. Number of protons is equal to 6. So N/P ratio is equal to 5 over 6 is equal to 0.823. Since the atomic number of carbon is 6, then its range is within 1 to 20. So, compare mo if 0.833 pinakuha mo is less than or equal to 1. And we know that 0.3833 is less than 1. Therefore, carbon-11 will undergo positron emission. Again, guys, yung positron emission occurs for the atomic nuclides with atomic numbers 1 to 40. Okay? Pag greater than 40 naman, electron capture sila. Okay? Hope that's clear. Now, let's proceed to this concept called the nuclear binding energy. So, the nuclear binding energy is the energy needed to separate a nucleus into its protons and neutrons. So, if mataas ang binding energy per nucleon, then the nucleus is stable kasi may strong attractive forces holding the protons and neutrons together. A high binding energy is needed to separate these forces. Now, the nuclear binding energy E is equal to delta mc squared, where delta m is the mass effect, which is equal to the sum of the total mass of individual particles in the atom. So that includes the mass of the proton, neutron, and electron, okay, total mass, minus actual mass of the atom. So that's given by the atomic mass or the molar mass. Okay? Yes. So, the concept behind mass defect is that the actual atomic mass, dito sa left, is less than the predicted mass na kinakalculate natin by adding the masses of the nucleons, which is neutron plus proton. Okay? Again, greater ang mass kapag inad mo together yung neutrons and protons kesa sa actual mass, which is given by the atomic mass. This is because some of the mass of the nucleus na-convert na kasi siya into binding energy. Okay guys, so let's answer. Determine the binding energy per nucleon for iron 56 with atomic mass of 55.93 AMU in mega electron volts. So the number of protons equal to 26, number of neutrons equal to 30. Now guys, I will also take into account the number of electrons. Kasi sa atomic mass na ito ng iron 56, okay, kasama ang mass ng electrons dito. Okay? So, look for the masses of proton, neutron, and electron. Kasi I highly suggest na i-memorize nyo na to. Pero when you memorize, okay lang. You can just determine it from your calculator. Okay, tuturuan ko kayo paano nyo makuha yung exact mass ng proton, ng neutron, and electron. Okay guys, tingnan nyo yung calculator nyo. So, ang gagawin nyo, kung canon yung calculator, shift, C value, tapos input 01. Okay? And then, equals, tapos equals ulit. And then you get the exact mass for proton. Okay? And that is in kilograms. Tapos, kung ano naman, kung electron, kung neutron, okay, Okay? 0, 2 naman yung input nyo. Equals ulit, then you get the mass of neutron. Then for electron, ganun ulit, shift, C value, then input 0, 3. Then you get the exact mass of electron. Okay? In kilograms yan lahat. So this is 0, 1, 0, 3, and neutron 0, 2. Okay? Pero guys, kung hindi canon yung calculator nyo, what you can do is shift, constant, 0, 1, 0, 2, or 0, 3, depending on anong hinahanap nyo, tapos equals. Okay? Tapos yun yung gamitin natin in calculating for the binding energy. Now guys, again, hinahanap ko ang masses ng protons, neutrons, and electrons because we have to find the mass defect. So again, the mass defect is equal to the total mass of the individual particles ng atom minus the actual atomic mass ni iron 56. Okay? So the total is yung individual particles na mahanap mo sa iron 56. So that's 26 protons times the mass of proton, 30 neutrons times the mass of neutron, plus 26 electrons times mass of electron. Okay? Minus the atomic mass, which is 55.93. Okay, again, tinake into account ko ang electrons. Now, solving for the mass defect, ganito siya guys. So this is again in total ng mga individual particles, total mass ng individual particles, ito yung actual atomic mass. Then convert the actual atomic mass to grams first, okay? So 1 gram is equal to 6.022 times 10 to the power 23 AMU. Okay, that's the Avogadro's number. So cancel mo lang to. Okay? Tapos, convert nyo ang grams to kilograms. So 1 kilogram is equal to 1,000 grams. Now, bakit natin convert to kilograms? Guys, tandaan, mas maganda is kung nagsasolve tayo in SI units. Okay, para consistent yung units mo. Ensure ka na SI units din yung makuha mong sagot. Okay? Again, SI units for mass is kilograms. Okay? And of course, yung mass din kasi ng mga proton, neutron, electron is in kilograms. So dapat consistent yan. Okay, kaya ba? Try nyo nga i-solve. So ginawa ko guys, ginamit ko yung exact value ng masses ng proton, neutron, electron, and ng Avogadro's. Okay? So, yung ko answer ay equal to 8.857 times 10 to the negative 28 kilograms. Okay? Baka guys, magkaka kayo, hindi exact yung nakuha natin. Okay? And that's because of the exact numbers or values na ginamit natin for the masses of proton, neutron, and electron, as well as the Avogadro's. That affects the mass defect. So, ang suggest ko sa inyo, it's better talaga to use the exact numbers. Don't worry naman guys, tuturuan ko pa kayo sa math recap natin, that's before physical chemistry, kung paano yung calculator tricks and how we can just easily input yung exact values ng mga constants such as the mass of proton, mass of electron, etc. Okay? And now, since we know the mass defect, we can solve for the nuclear binding energy, E is equal to delta m squared. So delta m is equal to 8.857 times 10 to the negative 28 kilograms times the speed of light, okay, 3 times 10 to the power 8 m over s squared. And that is equal to 7.97 times 10 to the negative 11 joules. So estimate lang to guys, okay? Again guys, nakita nyo, yung energy na units na nakuha ko is joules, which is SI, right? Sure ako na tama yan kasi SI yung ginamit ko all throughout. Okay? SI ito, and SI ito. That's why SI din yung nakuha kong units for the energy. And now, hinihingi ng problem is the molecular binding energy in mega electron volts. So let's convert joules to mega electron volts. So energy is equal to 7.97 times 10 to the negative 11 joules times 1 electron volts is equal to 1.6 times 10 to the negative 19 joules. So tandaan niyo yan. Again, 1 electron volts is equal to 1.6 times 10 to the negative 19 joules. That's why maka-cancel ko na si joules to get the electron volts. Then i-convert ko si electron volts to mega electron volts, where 1 mega electron volts is equal to 10 to the power of 6 electron volts. So maka-cancel si electron volts. Here, we get the units. We get the value for the nuclear binding energy in mega electron volts, which is 498 mega electron volts. Now, hindi pa tayo natatapos dyan. Guys, yung tanong, determine the binding energy per nucleon. Eh guys, ito kasi, for all particles to, all particles. Eh, gusto lang ng problem na ito ay the binding energy per nucleon. So, divide the nuclear binding energy to 56 nucleons. So, the 56 nucleons comes from the 26 protons plus 30 neutrons. Okay? Thus, the answer is 8.90 mega electron volts. Okay? Again guys, most likely mag-iba-iba yung sagot natin. Okay? Dahil sa units and sa decimal places ng mga values na nakuha natin. But yung tip ko dyan guys, pag sa board exam, it's best na, okay, use the exact values. Tapos, hindi nyo pa rin nakuha yung tamang sagot na nasa choices. Okay? Yung answer dapat is yung pinakamalapit sa isang choice. Kung si B, pinakamalapit sa nakuha yung sagot. Most likely yun na yung sagot. Okay? So guys, if you have any questions at all regarding the sample problem, I know it's challenging, feel free to message me. Now let's move on to nuclear radiation. Now the energy from nuclear radiation comes from mostly radioactive decay, but some of these nuclear radiation can actually be emitted from nuclear fusion and nuclear fission reactions. So there are 3 main types of nuclear radiation. So first is the alpha radiation, okay, as shown in your table 13. So it consists of 2 protons and 2 neutrons, like a helium. Okay? It is a heavy yet slow moving particle, as shown here, di ba? And its ionization power or its ability to remove electrons from atoms is high. However, its penetrating power is low. Okay, because it is unable to penetrate everyday materials gaya ng paper and the outer layers of skin. Next is, its applications include in smoke detectors, heart pacemakers, and space probes. Next, beta radiation is in the form of an electron or a positron. Compared to alpha particles, beta particles are lighter and faster. They have a moderate ionization power, and their penetrating power is moderate because it can penetrate air, paper, and a few millimeters of skin. Pero, kaya siyang mapigilan ng thin sheet of aluminum or vanadium. Its applications include medicine tracers and industrial processes. Lastly, the gamma radiation is in the form of gamma rays. So ito yung part ng electromagnetic radiation natin, which is high in energy. Its ionization power is very low, and its penetrating power is very high because it can penetrate many materials such as the human body or the skin. Okay? However, it can be stopped by dense materials like lead and concrete. So, applications ng gamma rays include telescopes and cancer treatment. Okay? So, a bit of history about nuclear radiation. Again, it is the energy released from the nucleus of unstable atoms. Okay? So, yung energy na ito ang nare-release ng mga radioactive na nuclides. Okay? So, over the century, ang dami na ng advancements on nuclear chemistry and nuclear radiation. Noong 1896, Henry Becquerel discovered the natural radioactivity through uranium salts. he also invented the concept of the rate of radioactive decay. So sa kanya galing SI unit ng rate of radioactive decay, which is 1 becquerel, which is equal to 1 disintegrations per second. Okay? Or 1 decay per second. In 1898, Marie Curie and Pierre Curie discovered polonium and radium, which then coined the term radioactivity. With this, the conversion of the unit for the rate of radioactive decay is also invented, where 1 curie is equal to 3.7 times 10 to the power of 10 becquerel. Guys, dapat memorize nyo itong dalawang to, okay? Lumalabas talaga to sa boards, promise. Okay? I mean, minsan kailangan nyo i-convert into curie yung sagot nyo. Okay? Again, 1 becquerel is equal to 1 disintegrations per second, and 1 curie is equal to 3.7 times 10 to the power of 10 becquerel. Next, in 1911 naman, Ernest Rutherford developed the nuclear model of the atom, and he studied alpha radiation through the golden foil experiment. And in 1945, ito yung sa Oppenheimer, guys, the Manhattan Project scientists used nuclear fission in the invention of atomic bombs, which consequently devastated Hiroshima and Nagasaki. Ito na yung plot ng Oppenheimer. Okay? And one fun fact lang pala about Marie Curie. Okay, did you know that to this day, many of Marie Curie's personal belongings, kaya ng notebooks niya, lab equipment, radioactive pa rin hanggang ngayon and are stored in lead-lined boxes. Diba? Ganun siya dedicated sa work niya on radioactivity. Now, let's proceed to the types of radioactivity. The 5 types of radioactivity include alpha decay, beta decay, positron emission, gamma emission, and electron capture. So, again guys, in radioactive decay, it occurs when an unstable nucleus loses energy by the emission of nuclear radiation. So, para masabi natin radioactive ang isang nuclide, okay, it has to emit nuclear radiation. So, in alpha decay, alpha particles are emitted from unstable nucleus. Beta particles naman in beta decay are emitted from unstable nucleus in the form of beta particle or electron. In positron emission, the proton in the nucleus transforms into a neutron, emitting a positron, which is the beta plus, and a neutrino. Guys, familiar ba kayo sa neutrino? So, ito yung symbol. Okay, ganyan. So, it's a elementary subatomic particle with no electric charge and very little mass. Ito ang symbol niya. Now, in gamma emission, gamma rays are emitted from unstable nucleus during high energy transitions. Ito yung symbol niya. And lastly, in electron capture, the electron from the inner shell, let's say nucleus to, tapos ito yung inner shell, may electron ka, na-absorb siya ng nucleus. This results in the conversion of a proton in the nucleus into a neutron. Okay? So, with that, this table summarizes the types of radioactive decay. So first, for alpha decay, the involved particle is an alpha particle. So ito yung 4,2 alpha or 4,2 helium. An example of this is the alpha decay of uranium-238. As you can see here, it results in the emission of an alpha particle and the formation of a daughter nuclide. Okay. Now, tingnan nyo guys, dapat balance ang left side and right side ng nuclear equation na to. Meaning, dapat equal pa rin ang number of mass numbers and ang atomic numbers. Okay? As you can see, sa left-hand side, ang total ay 238 ang mass number. So sa right-hand side, tama naman, 234 plus 4 is equal to 238. Ganun din, the atomic number, dapat equal ang atomic numbers on both sides. For uranium, it's 92. For thorium and alpha particle, 90 plus 2 is equal to 92. Okay? Now, here's a technique para malaman nyo kung anong type of radioactive decay ang nangyayari. Let's look at the daughter nuclide, thorium, or 234. Let's compare it with uranium-238, the original nuclide. So si thorium-234, nag-decrease by 4 ang kanyang mass number compared to uranium. And its atomic number also decreased by 2 compared to uranium. Okay, again, for alpha decay, decreased by 4 ang mass number, decreased by 2 ang atomic number. Next, that beta decay. It consists of a beta particle, 0, -1 beta, or 0, -1 electron. An example of this is the beta decay of uranium-235. This results in the emission of a beta particle here, in the formation of a new daughter nuclide. Okay, again, dapat equal pa rin both sides, the mass numbers and atomic numbers. So, another technique, let's look at the change in the atomic number and the mass number of the daughter nuclide. So, for the Neptunium daughter nuclide, the mass number, or A, hindi nagbago. It is unchanged. But its Z, or atomic number, increased by 1 compared to the uranium atom. Okay? Next, for gamma emission, the particle involved is a gamma ray. So, ito yung form niya. An example of this is the gamma emission of technetium-99 metastable, okay, to form a more stable nuclide of technetium. Okay? And with that, a gamma ray is emitted. Now, for gamma emission, guys, walang nagbago sa mass number and atomic number. Okay? Next, for positron emission, a positron is involved. Ito yung form niya, 0 plus 1 beta or 0 plus 1 electron. An example of this is the positron emission for the magnesium atom, magnesium-23, okay? As you can see, may positron na na-emit. Okay? And a daughter nuclide, sodium-23 is formed. Compare natin siya with the original nuclide. Yung A niya, or yung mass number niya ay hindi nagbago. But its atomic number decreased by 1 compared to magnesium. Lastly, we have electron capture. It involves electron, the capture of an electron, and the emission of a gamma ray. So an example of this is the electron capture of strontium-80. It captures an electron to result in these products. So may gamma ray emitted ka, and daughter nuclide rubidium-80. Let's compare, guys, the A and Z for rubidium, the daughter nuclide. So compare with strontium, unchanged ang kanyang mass number, equal pa rin sila, and decreased by 1 naman ang kanyang atomic number compared to strontium. Okay? Nung paano ko tayo memorize, guys, kayang-kaya niyan. Basta isipin nyo lang, pag alpha decay, decrease by 4, decrease by 2, sila lang yung ganun. Sila lang yung special na may 4, 2. Pero si beta decay and si positron emission electron capture, sila yung may increase or decrease by 1 ang atomic number. Pero hindi nagbabago ang mass number. Si gamma emission naman, walang pagbabago. Tandaan nyo lang, guys, kailangan lang na may ma-emit na gamma ray for gamma emissions. Ilalagay nyo pa rin to. Okay? Para balance yung equation and tama yung reaction. Okay? So again, guys, to summarize, alpha decay, siya lang yung may decrease sa mass number by 4 and decrease sa atomic number by 2. Now, si beta decay, siya lang ang walang change sa mass number and nag-increase ang atomic number by 1. Si positron emission naman, electron capture, unchanged ang mass number, and silang dalawa, nag-decrease ang atomic number by 1. Ang difference nila, again guys, electron capture, may captured electron ka and emission of gamma ray. For positron emission, may emission ka ng positron. And lastly, for gamma emission, walang nangyari sa A and Z, but you always have to add this, okay? The gamma ray. Now, that's clear, and with that, let's apply that to this sample problem. Balance the following nuclear reaction equations presented below. Okay guys, so I'll give you some time to answer. Pause this video first. Okay, so let's balance these equations and answer. Number 1, for californium-254, guys, actually, this is a nuclear fission reaction. Okay, so all we have to do is balance from the left side and from the right side. Dapat equal ang mass numbers and atomic numbers. So, sa atomic numbers, equal naman sila dalawa, right? Now, sa mass numbers naman, kulang ng tatlo. See? Right side. That's why, all we have to do is just simply multiply by 4 yung emitted neutron. Okay? Para balance yung equation. So, answer is 4. Number 2, we have no idea what type of radioactive decay nangyari. So, all we have to do first is just balance. Okay? So, sa left side, the total mass number is 8. Sa right side naman, 4 lang. So, kulang ka ng 4. So, maglalagay ka ng 4. Tapos, check mo yung atomic numbers. Sa left side, 3 plus 0, 3 ang total. Sa right side, 1 plus 0, 1 ang total. So, kulang ako ng 2 pa para maging balance. Okay? So, familiar na to. Dapat, di ba? Gagawin ko, tingin HT to. So, balance na ang equation. So, this is basically the alpha decay of lithium atom. Okay? So, number 3, wala din tayong idea kung ano yan, guys. Okay? All we know that this is the daughter nuclei. And this is the parent. Ang gagawin ko, fill in the blanks pa rin. Now, let's look at the mass number. Sa left side, 37. Sa right side, 37. So, the mass number is 0. For the mystery blank. Okay? Next, for the atomic number, okay, for argon, yung daughter nuclei 18. For potassium, yung parent 19. So, kulang ako ng ilang? Ilan sa atomic number? Tama, 1. Ayan, familiar na ba, guys? Ano yan? Tama, beta. So, the answer is 0,1 beta. This is the positive emission of potassium 37. Okay? Again, all you have to do is balance. Okay? And another technique, of course, is sinabi kong change in A and Z. So, again, yung A is unchanged. Tapos si Z naman, decreased by 1. And that corresponds to the positron emission. Kaya nag-add ako ng positron. Okay, next item. So here we have bismuth, and it has a doctor nuclei polonium. Okay, let's answer. So we see na 215 yung mass number sa left side. Sa right side naman, 215 din. So, yung i-add ko na particle, 0 yung kanyang mass number. Okay, next, for the atomic number, sa left side, it's 83. Pero sa polonium sa right side, 84. Sobra ka. So, kailangan mo magbawas para equal sila na 83. So, I'm gonna add negative 1 here. Yan, familiar na ba, guys? Tama, this is a beta particle. So, this shows the beta emission of bismuth 250. Ayan, another one. So, ang clue natin dito, guys, is meron tayong alpha decay of radon. Kasi meron tayong alpha particle na na-emit dito. So, all we have to do is find the daughter nuclei. So, kailangan mo lang talagang i-balance. Okay? Nagawin natin, first sa mass numbers, 222 minus 4, 218. 86 minus 2, 84. Tapos, hanapin nyo guys, periodic table, sino ang may atomic number equals to 84? Sino kaya, guys? Tama. See? Polonium. Okay? Again, this is the alpha decay of radon 222. Okay, last. Ito naman, given na yung daughter nuclei, so we don't know what type of decay this is. So, kailangan muna natin i-balance yung equation. So, mass number unchanged for both sides. So, 0 yung mass number. Then, compare the atomic number. Nag-increase by 1 ang atomic number ni AM. So, kailangan magbawas para equal silang 94. So, negative 1. What is this, guys? Tama. Beta particle na naman. So, this is the beta emission of Pu. Yan. So, this is the answer, guys. Hope you got it right. Let's proceed. The application of radioactive decay. So, these are summarized in table 15. So, carbon 14 is used in carbon dating, uranium-238 for uranium-lead dating, uranium-235 for nuclear power generation, H3 for the water content in the body, cobalt-60 for cancer treatment, iodine-131, diagnosis of thyroid defects, thallium-201, heart scan, technetium-99 metastable, brain, liver, and kidney scans. Actually, guys, parang sa previous board exams, parang lumabas yung technetium-99 metastable. So, maganda rin na i-memorize ito. Okay? And did you know bananas are slightly radioactive? So bananas, they contain potassium-40. It is a naturally occurring isotope that emits low-level radiation. Kailangan mo kumain about 10 million bananas at once para mamatay from radiation poisoning. Radiation has never been so appealing. Now let's proceed to the kinetics of radioactive decay. So radioactive decay is a first-order reaction where the rate of decay is dependent on the amount of radioactive material. Here, we solve for the half-life, or the time it takes for half of a radioactive substance to decay. Based on this graph, okay, initially you have 10 grams of cobalt-60. After one half-life, which is equivalent to 5.27 years, okay, 5 grams is left from the cobalt-60. Okay? And then after another half-life, 2.5 grams na lang ang natitira for cobalt-60. Okay? Which is half ng 5 grams. Okay? So the following equations shown in table 16 are used in calculating for the kinetics of radioactive decay. So, guys, ang equation na to, it just states that the change in the amount of the radioactive material N over the change in time is equal to the negative of the decay constant times the amount of the radioactive material na naiwan. And then this is simplified to this equation for first order reactions. Ln, N, which is the amount remaining after time t, over N naught, which is equal to the initial amount, is equal to negative KT, where K again is the decay constant, and T is the time lapsed. Okay? Now here, guys, ang calculation na to, okay, this is for first order reaction, okay, where Ln2 is equal to KT1. Diba? Very easy lang. And lastly, we can also find the activity. So the activity is the rate at which the substance decays. Okay? Now, again, guys, yung rate at which the substance decays, ano kaya ang kanyang unit? It's disintegration per second. Again, ang unit ng activity, disintegration per second, because it is the rate at which the substance decays. Okay, so it is calculated through A is equal to decay constant times the amount of radioactive material remaining. Okay, the activity before and after decay, pwede natin mahanap through the equation Ln A over A naught is equal to negative Kp. Okay, although radioactive decay mainly occurs in first order reactions, sometimes yung mga nuclear reactions, okay, they may occur in zero or second order. Other nuclear reactions, okay, such as nuclear fission, pwedeng zero or second order. So shown in table 17 are various equations used in calculating for the rate, amount of radioactive material, and half-life in radioactive decay and nuclear reactions. Okay, so memorize nyo lang to guys, yung mga general equations na to. Pero basically, for zero order, rate is independent of concentration. Tapos, yung initial and remaining amounts of the radioactive material present, itong A, is solved using the integrated rate law. Lastly, the half-life for a zero-order reaction is directly proportional to concentration. Ganyan, okay? And then so on and so forth for the first order and second order. Guys, we will delve deeper to reaction kinetics once we reach this topic in FEChem, okay? But for now, kindly make sure lang talaga na memorize nyo itong half-life equations na ito. Because last year raw, sa Inorg boards, may pinapahanap raw na half-life ng isang second order radioactive decay. So it's best to memorize the half-life equations for zero, first, and second order reactions. Okay? I hope that's clear. Now let's proceed. Okay, time to answer the sample problem. Okay, pause nyo muna guys, try to answer on your own. Okay, let's answer. So here we are given the half-life of iodine-131, which is equal to 8.1 days. Also given how long it will take for 3/4 of a sample to decay. So we're finding the time it takes for 3/4 of a sample to decay. So first, let's solve for the decay constant using the half-life equation. Ln2 is equal to Kp1. Okay, so transposing, we get K is equal to Ln2 over 8.1 equals to 0.0856. Then that's the value for the decay constant. Next, let's now find the time it takes for 3/4 of a sample to decay using this equation. Ln n over n naught is equal to negative Kp. Transposing, we get this equation. Now let's analyze this guys. So 3/4 daw ang nag-decay. Let's say we have this amount of radioactive sample ng iodine-131, right? And then ito yung amount na nag-decay. So meaning, ang natira ay 1/4 of the initial sample of iodine-131. And that is equal to the N, which is the remaining amount of radioactive material after time T. Okay? So, meaning yan, N is equal to 1/4 N naught over N naught. Okay? Solving, we cancel N naught. We get Ln 1/4 over negative 0.0856. Ito yung tama guys ha? Negative 0.0856. And you get T is equal to 16.2 days. Thus, the time it takes for 3/4 of a sample to decay is 16.2 days. Second problem. Okay, medyo mas mahirap to, so let's do this together. The half-life of iodine-131 is 8.02 days. What is the activity in curie of a 1 milligram sample? So we're given again the half-life. And we're also given 1 milligram here. Makuha natin ang amount of radioactive material. So first, find the decay constant through this equation. Half-life equation. K is equal to Ln2 over 8.02 days is equal to 0.0864. Okay guys, may introduce ako na units. Ito yung units ng ating K. It essentially quantifies how many atoms ng iodine-131 ang nagde-decay per day given a certain number of atoms. Again, K, it quantifies ilang atoms ang nagde-decay per day. Nagde-decay per day. Okay? So pwede rin guys, ganito siya. Is in atoms per second. Kung ang given na half-life is in seconds. But in this case kasi guys, days ang binigay. Kaya in terms of days, ang decay constant na ito. Okay? Now, let's convert the decay constant, okay, from days to seconds. Bakit guys? Para yung result natin mamaya sa ating mga calculation ay in SI units. Tandaan, SI units ng second or ng time is seconds. Okay? So, 0.0864, this integration per atom times day. So, convert days to hours first, where 1 day is equal to 24 hours. So, cancel days. Then convert hours to seconds, where 1 hour is equal to 3,600 seconds. So, cancel hours. And here, we get the value of the decay constant in terms of this integration per atoms times second. Okay? And now, we are ready to find the activity of a 1 milligram sample. So, activity is equal to Kn. A is equal to K, ito, times 1 milligram. Again, dito galing yung N mo. Then convert this first to grams, guys. So 1 gram is equal to 1,000 milligrams. Cancel milligrams. And then convert it to mole. So the molar mass of iodine-131 is 131 given dito. So 1 mole is equal to 131. Cancel grams. Then you cancel the moles here. Nan bakit? Okay, so kinonvert natin yung moles to atoms. Again, ito guys is Avogadro's number, which is equal to 6.022 times 10 to the power 23. Right? Kasi guys, ang decay constant is expressed in atoms. Again, expressed in atoms ang decay constant. Kaya kinonvert ko rin ito into constant. So the answer is, ayan, the activity is equal to 4.5985 times 10 to the power 12 becquerel. Binigay ko na agad yung becquerel guys, but that is still equal to this integration per second. And tama naman guys, di ba? Kasi na-cancel na itong atoms, cancel. Ang naiwan mo na units activity is this integration per second, which is just equal to 1 becquerel. And then, kailangan ng problem is curie ang activity. So, we convert 1 curie. So, we convert becquerel to curie, where 1 curie is equal to 3.7 times 10 to the power 10 becquerel. Thus, the value for the activity of a 1 milligram sample is 124 curie. I know guys, medyo overwhelming siya, pero alam niyo yun, ang bagal-bagalan niyo lang. Okay, kaya na to. Okay? Ang maganda kasi dito guys, repetition and practice. Okay? Para maging pro kayo dito. Okay? So, this table summarizes the various types of nuclear reactions. So, dinaanan natin ang radioactive decay. There's also bombardment reaction. And now, we will discuss the other types of nuclear reactions, nuclear fission and nuclear fusion. Okay? So, these are the two types of nuclear reactions. For nuclear fusion, okay, they have different definitions, okay, but both of them releases very large energy. Nuclear fusion needs extremely high temperature and pressure, and nuclear fission requires a heavy neutron. And these are the various reactions ng nuclear fusion and fission. Okay? Gusto dapat memorize natin to, okay? Because ito yung pinaka-typical na reactions for each of them. Nuclear fusion occurs for sun, stars, and hydrogen bombs, while nuclear fission occurs for nuclear reactors and atomic bombs. So, this is an example of a nuclear fission reaction. So, cool, right? Okay. Specifically, nuclear fusion is a process in which two light atomic nuclei magko-combine sila to form a heavy nucleus, and that releases a very large amount of energy. Ang example natin dito is deuterium and tritium. They combine, they form a heavier helium atom, and that releases a huge amount of energy. And this typically occurs in the sun and stars. Okay? Again, extremely high ang conditions niya to overcome the electrostatic repulsion between positively charged atomic nuclei. O ito naman guys, ano kaya yan? It's the nuclear fission for uranium-235. First, yung yellow na neutron na yan. Okay? Sige, ulitin natin. Now, yung yellow na neutron na yan, it will strike the nucleus of uranium-235, i-attack niya, quote and quote. And this results in the formation of an unstable nuclide, uranium-236. That's very quick lang ang formation ni U-236. Di mo nga siya makikita dyan, di ba? So it will quickly undergo fission to release energy and produce smaller nuclei, gaya ni barium-139 and krypton. Okay? And additional neutrons are also produced. And this can trigger a chain reaction of fission reactions. Again, need mo ng neutron that quote-unquote attacks uranium for it to form the more stable Doppler nuclides such as barium and krypton, and additional neutrons na pwede mag-initiate ng another nuclear fission reaction. Okay? So here we see that a neutron is needed to kickstart the reaction. Now, nuclear fission reactions can be controlled in nuclear reactors or uncontrolled, such as in atomic bombs. Okay, so for us to know more about the nuclear reactors, okay, let's watch this video.
Nuclear power is one of the ways humans produce electricity. The term nuclear power refers to the source of this energy, the nucleus of atoms. Here's how it works. Inside a nuclear power plant is a nuclear reactor where heavy elements like plutonium or uranium fuel nuclear fission reactions. These elements are contained in fuel rods. The fuel rods, where the fission chain reactions occur, create enormous amounts of heat energy. They are submerged in a vat of cold coolant, usually water, which is then heated. The heated coolant moves through a pipe into a steam generator. There, the heat energy carried by the coolant turns water to steam. Together, the reactor, steam generator, and all of their connecting pipes are known as the primary system. The steam moves through a pipe to a turbine, which is the start of the secondary